based on ODE solvers. For those of you who haven't thought about ODEs since undergrad, here's a quick review. The setting is that there's a vector-valued latent state Z, such as the position and velocity of a system of particles or a concentration of chemicals in a reaction. This state changes continuously with time, and a function f defines the derivative of this state with respect to time. This gradient field can vary both with the current state and time. What we usually do with ODEs is solve initial value problems. What this means is that you're given this state at some time t0, and you need to compute the future state at some time t1. Evaluating this state exactly requires integrating the derivative of the state through time, and usually has to be done approximately with a numerical solver. The oldest and simplest numerical solver is Euler's method, which simply takes many small steps in the direction of the gradient at the current position. Euler's method is generally considered a poor solver because it accumulates error at every step. Fortunately, there's been hundreds of years of progress in ODE solvers since then. Modern solvers have sophisticated evaluation and extrapolation strategies and provide error guarantees by adapting their step sizes to the difficulty of the problem. Many people have noticed that there's a close connection between residual networks and Euler integrators. Let's look at the code for a Resnet. First, you need to define a Resnet block, which is usually some small neural network. This defines the update to the hidden units at every layer. Then, to build the rest of the Resnet, you simply compute the update at every layer and add it to the current hiddens. This looks just like Euler integration. And on the right, we can watch this algorithm being executed one layer at a time. So I should mention that there's a lot of related work in this area on the connection between neural networks and ODEs. In fact, in the early days of neural network research, continuous time networks were often taken as a natural starting point because real brains are also continuous time systems. Notably, recently it was used to suggest some new neural network architectures as well as new training methods. But how far can we take this connection between neural networks and ODEs? Looking back at the code for a Resnet, we can actually make one simple change to make its dynamics continuously defined with depth, like an ODE. So looking at the Resnet block, we can simply feed the current depth to the Resnet block and use the fixed set of parameters for the entire depth. This change means that the dynamics are now defined even between layers and can change continuously with depth. So this model actually now defines an ordinary differential equation. But we're still using primitive Euler's method to solve it. However, we're free to replace Euler's method with a more sophisticated adaptive solver. We can replace that entire for loop with a single call to any ODE solver, running the dynamics from depth t0 to depth t1. And this solver is free to evaluate the dynamics network anywhere it wants in order to get the final answer in as few steps as possible. So this is what this looks like. We call this model an ODE-net. So how do we train these networks? We somehow have to get the gradient of the objective through the ODE solution. You might think that we're going to simply backpropagate through the operations of the ODE solver, but this is a bad idea for two reasons. First, because storing the intermediate operations of the solver adds high memory costs. Second, this approach adds numerical error to the gradients. More generally, we should always try to approximate the exact derivative and not to differentiate the approximation. So how can we take the exact derivative through an ODE solution? Well, on the left, we have the standard reverse mode chain rule for a neural network. And if we take the continuous time limit of these equations, we recover the adjoint sensitivity equations, which were actually developed in the 60s. We can use automatic differentiation to define these adjoint dynamics, and then integrate them backwards in time using another call to an ODE solver. So we're using automatic differentiation to do this automatically for any differentiable function. So this second ODE solver runs backwards in time. Surprisingly, this whole procedure can be done with constant memory costs. This is because we don't store the intermediate activations. We just reconstruct them as we go by running the original system backwards in time. Recent work on reversible residual networks constructed neural networks that did have the same constant memory property, but it required restricting the architecture of the layers of the neural network. Our approach works automatically for any differentiable dynamics. So now we have a new differentiable model component that we can put in our models. Anywhere we have a set of Resnet layers, we can replace them all with a single ODE-net. Besides constant memory cost, another advantage of ODE-nets is that they generally require fewer parameters than Resnets. Because the network dynamics change smoothly with depths, the parameters of nearby layers are automatically tied together. This table shows us using ODE-nets to do classification on MNIST and achieving the same test accuracy with about a third of the parameters as Resnets. So one interesting question is, how deep are these models? And the funny thing about ODE-nets is that they don't have a fixed number of layers. The best analogy to depth in these models is the number of evaluations of the dynamics network that the ODE solver makes. So we don't actually have to specify the depth of these models. We just delegate that detail to the ODE solver. For instance, on the right, we show the trajectories corresponding to different inputs in a toy ODE-net. The circles show evaluations by the solver. You can see that the simple dynamics in the center require fewer evaluations than the more complicated dynamics on the sides. We found that the dynamics actually became more demanding to compute during training. Here we show the average number of dynamics evaluations required by the ODE solver increases during training. So the downside of these models is that we can't directly control the time cost of the model during training, and the final models often end up being more expensive than the corresponding Resnet by about a factor of 2 to 4 times. Although the optimistic way to think about this is that the models are learning to be deep. Interestingly, recent work by Chang et al. Used the theoretical connection between Resnets and ODE solvers to suggest a scheme for gradually increasing the depth of Resnets during training, whereas here this happens automatically. So although we can't control the time cost of the model during training, we can control the time cost at test time. A nice feature of modern ODE solvers is that they can explicitly trade off the speed of evaluation and the precision of the answer. In this figure, the blue line shows the error ceiling, or the tolerance that we've given the solver. And when we plot the actual errors in a real ODE-net, they all are within the error tolerance. Now, we can loosen this tolerance further, and the time cost of the network decreases while the solver still meets its tolerance. Compared to using low precision floating point numbers, this is a more fine-grained way to trade off between speed and precision. Now that we can fit ODEs with gradient descent, we can use this to build better time series models. Specifically, we can train physics-style models in which a latent system has continuous time dynamics. We can also add complicated noise models to the observations. Unlike recurrent neural networks, these models have a well-defined state at all times, and they decouple the specification of the system dynamics from inference about the latent state. This lets us handle data that arrives at irregular intervals in a principled way. Here we show results on a toy problem where 2D observations are made at irregular times. On the right, you can see that the latent dynamics model smoothly interpolates between the data and extrapolates beyond it. On the left, the recurrent neural network doesn't have a well-defined state between observations, and it also extrapolates poorly. This is just a proof of concept, and we're working on scaling up these models and extending them to stochastic differential equations. For the computational neuroscientists in the room, you can also add Poisson process likelihoods to this model and train it all at once. This is a general way to define, or Poisson processes are a general way to define a distribution over the times at which we're likely to see data. We hope to use this, for example, for medical records. In that setting, the fact that someone came to the hospital at a particular time tells you a lot about their latent state. So the biggest benefit so far to moving to a continuous time turned out to be for density modeling. The foundation of models like normalizing flows or real MVP is the change of variables formula. It says that the change in density due to mapping through a function is given by the determinant of the Jacobian of that function. But what if we make an instantaneous or an infinitesimal change to a variable? Then how does the density change with time? In our paper, we proved that the derivative of the log density with respect to time, or depth, is given by the trace of the Jacobian. We call this the instantaneous change of variables formula. Trace is a much cheaper, a cheaper operation than the determinant, and this formula doesn't require that our neural network is invertible. We used this theorem to build a new class of generative density models, continuous normalizing flows, that continuously transform a simple distribution into a complex but normalized one. Continuous normalizing flows have a lot of nice properties. They give exact normalized densities, and because the dynamics are reversible, we can train them directly from data samples, unlike traditional normalizing flows. There's also no need for a recognition network or a discriminator. You can train this generative model with just plain SGD. There's also no need to restrict the network architecture or partition the dimensions. So here's a toy example of a transformation learned directly from data shaped like a leaf. What? No. Oh, no. OK. There we go. The model continuously transforms a Gaussian into the data density. In follow-up work, we brought the cost of estimating the density down to linear time for any dynamics network architecture. This let us scale up so far to medium-sized images. Here, you can see it continuously transforming Gaussian noise into images. It also matches the state-of-the-art for efficiently sampleable density models. Of course, it's still early days for this model class, and the computational cost is greater than that of GLOW or real MVP. We're working on regularizing the dynamics to encourage fewer evaluations. We just released PyTorch code for all of these models. We also released a set of differentiable adaptive step solvers that use the adjoint method that we explained to give numerically stable and constant memory derivatives. This includes Runge-Kutta and adaptive order implicit atoms. And you can mix and match these ODE solvers with any other differentiable model component. To summarize, we introduced a new family of neural network architectures that have continuous depth. These networks adaptively compute their output, can be trained with constant memory cost, and let the user trade speed for precision in a fine-grained way. We showed how to build time series models that can handle arbitrary measurement times. And finally, we derived a new class of efficiently invertible generative density models. I'd like to thank my students Ricky Chen, Yulia Rubanova, and Jesse Betancourt. Thank you.